You know, we're surrounded by things we trust our lives with every single day, our cars, planes, you name it. But what happens when one of those objects has a hidden flaw, a tiny, microscopic secret that could lead to, well, catastrophic failure? Today, we're putting on our detective hats and going full forensic investigator on a really critical manufacturing defect.
So, I want you to think of this less as an engineering problem and more like a microscopic crime scene. Our mission, should we choose to accept it, is to follow the clues and uncover a flaw that's hiding in plain sight.
All right, so our crime scene is the factory floor, and the victim? It's a complex, super high-strength aluminum gearbox made for a high-end commercial vehicle. The problem is, these critical components are failing, and nobody has a clue why. And believe me, the stakes are incredibly high.
Okay, here is our first piece of evidence. These parts, they look absolutely perfect coming off the production line. But later on, during a really precise milling process, nearly 1 in 5 of them just cracks. An 18% failure rate isn't just a little problem, it's a full-blown manufacturing disaster. It's pointing to something deeply, deeply wrong that no one can see.
And this is where we get our first big break in the case. See, the company runs 3 supposedly identical presses, but look at this. Press C has a defect rate of 26%. That is way higher than the others. Right away, this tells our investigators that the flaw probably isn't in the raw material or the design itself. No, it's tied to a specific process happening on one specific machine.
So after some really careful analysis, the engineers finally give our culprit a name, sfogliature. It's an Italian term for a specific kind of delamination, or flaking. And trust me, this isn't just a simple crack. It's something much, much sneakier.
So what is it exactly? Well, imagine a solid piece of metal suddenly deciding to separate into these ultra-thin layers, almost like the pages of a book. These layers create these hidden weak planes running right through the material. So under stress, the part doesn't just crack, it literally peels apart from the inside out.
And here is why this defect is basically the perfect crime. It is often completely invisible right after production. I mean, it can pass every single standard quality check, no problem. And then, it just shows up later, maybe when the part is being machined, or even worse, when it's out there in the real world inside a vehicle. It's a ticking time bomb hidden right inside the metal itself.
So now that we've identified our defect, it's time to bring in the suspects. In manufacturing, failures like this usually boil down to one of 4 main areas. So let's take a look at the lineup. Okay, our 4 prime suspects are: Number 1, thermal issues. Is the part heating up or cooling down too fast or unevenly? Number 2, flow dynamics. Is the liquid metal being injected into the mold too violently? Third, metallurgy. Is there something actually wrong with the metal alloy? And finally, mold design. Could the shape of the mold itself be creating the problem?
Pretty quickly, the investigation starts to zero in on the 2 leading suspects. On the left, you've got thermal issues. If that molten metal gets above 700 degrees Celsius or cools down unevenly, it creates massive internal stress. Then on the right, you've got flow dynamics. If the metal is injected faster than 50 meters per second, it creates turbulence that can trap tiny air bubbles and impurities, and that's what creates those weak layers.
All right, at this point, the engineering detectives bring out the big guns, the high-tech forensic tools. They know they need to look inside the metal itself, all the way down to the microscopic level to find some real hard evidence. And their process is super methodical. First, they crunch all the numbers, analyzing all the production data they have. Next, they use non-destructive tools, things like ultrasound and X-rays, to scan the parts without having to cut them open. And then, finally, they slice up the failed components and stick them under a powerful microscope, hunting for that one final clue.
And under the microscope, they find it. The smoking gun. Right there, along the fracture lines, they discover these thin films of aluminum oxide, which is basically rust, and these brittle iron compounds. These are the impurities, the foreign bodies that got trapped between the layers of metal. The evidence is crystal clear. Something is contaminating the aluminum while it's being injected. But what's causing the contamination? I mean, how is it getting in there? To find the answer, the team turns to the ultimate forensic tool, computer simulation. They basically recreate the entire injection process inside a supercomputer, which lets them see what the naked eye could never, ever witness. You have to understand, these simulations let them peel back the steel walls of the mold and just watch, millisecond by millisecond, as this molten aluminum fills the cavity.
They're looking for that exact moment, the instant where everything goes wrong.
And there it is. The simulation reveals that in certain critical spots in the mold, the liquid metal is moving at over 80 meters per second. That's nearly 180 miles per hour. Remember that safe speed limit we talked about, 50 meters per second? This is blowing way, way past it. It's causing absolute chaos inside that mold.
So here's what the simulation showed them so clearly. On the left, that's the before. You've got this high-speed, turbulent flow that's like a raging river, just churning the metal, folding air and oxides into it, and creating those deadly weak layers. And on the right, the solution. By slowing down the injection, you get a smooth, orderly, laminar flow. No chaos, no trapped impurities. Case closed.
So, with the culprit identified and a full confession from the simulation, what's the verdict? What are the big lessons we can actually take away from this whole investigation?
Well, the biggest lesson is that this failure wasn't caused by just one thing, but a mix of factors. But the main one was that insane injection speed. The smoking gun was definitely that turbulent flow. And the solution? It was actually surprisingly simple. Just reducing the injection speed by about 30% got rid of the chaos. It's a really powerful reminder that in high-precision manufacturing, control is almost always more important than speed.
And you know, this whole thing leaves us with a final thought. This entire high-stakes drama of fluid dynamics and thermal stress, it all played out in about 65 seconds, totally invisibly, just to create one part of a machine. It really makes you wonder, right? What other incredible unseen stories are locked away inside the everyday objects all around us?